the seminar series. There is also a student of this program. I don't remember your name. Mark is working with Victor. And finally, well, the Professor Plastina from La Plata, so will be here for 4 months. 1 month. 1 month, so welcome everybody. Thank you.
And Francesco Plastina will be here also 1 month. He's visiting us 1 month. So I just introduce him. So Francesco is from the Università della Calabria. He got his PhD in 2000 with Professor Viterno and Falcone, and then moved to Esposo to work with Professor Palma in Palermo, and with Rosario Fazio at the Normale Superiore in Pisa. He's an expert in quantum information, quantum correlation in mesoscopic and nanoscopic systems like optical, magnetic, solid state, and atomic systems. And today he's going to speak about decoherence and non-Markovianity. Just because he was also visiting, the rest was also visiting in Seoul, Mansum Choi. They discovered visiting here. And
long time
ago in Seoul, and was also visiting New York University and Tokyo University, and now Palma for bonus. Okay.
Thank you, Roberta, and good afternoon, everybody. Thank you for the opportunity for being here in this nice place. Beautiful moment in Scotland. Okay, I will give you a short discussion of the newly introduced concept of non-Markovian quantum systems. I didn't know how much you are familiar with this stuff, so I really a very plain and very logical segment, essentially taken from say lectures given first of all, let me thank all the people I've discussed and worked on this subject. Many people from Edinburgh University, University in Edinburgh, the group of Sabrina Maniscalco, people in Belfast, the group of Mauro Paternoster here, also some people from Oxford and Cork in Ireland, which are these 2 guys here that you probably don't see, and you will probably see them drinking here somewhere in Ireland, etc. And also people from my group, the Università della Calabria, in particular Tony and Salvatore, which is Chernobyl stop. This problem, essentially. So here is enough time to talk. I will start from the beginning, really, discussing open quantum systems and in particular Markov processes, and then non-Markovian dynamics, which is quite common, but not so well understood. And then I will introduce a measure for non-Markovianity. I should say from the beginning that I don't like non-Markovianity as a kind of negative statement. Okay? I would like to use a positive statement, which would be memory keeping. So from time to time, although the great majority of physicists working with this stuff call it non-Markovianity, I would prefer to call it, say, memory keeping dynamics. And the idea of keeping memory of what happened before is just what will bring us to define a measure for the amount of non-Markovianity which is present in academic dynamics. And then I will discuss some application. The first one to pure dephasing dynamics, which is a particular case of decoherence in which the system undergoing interaction with an environment is not losing energy, but rather losing coherence only, which is a typical quantum behavior. And then, give a specific example in which the environment can become critical or show specific features. In particular, the first 2 points are really general. I took them and essentially I stole them from a pure presentation from Professor Royer from Fribourg University. And the third part is essentially contained in a paper we have written that just appear in PRA, and then the other part is, say, example. I don't know if I have time to discuss many examples, but we have done a lot of paper in this on this subject and discussed many cases in which you have a system, in this case, zero dot there, coupled with an environment which can be a Fermion environment or a spin environment or a bosonic environment, depending on the cases. I don't know if I have time to discuss all this stuff, and Roberta to stop me whenever. The main message is essentially related to the general definition of this, of what is non-Markovianity in the quantum case and how to measure it. Okay. So first of all, we have to discuss open quantum systems, and this is say a picture that Professor Steinholm typically employs to describe what is what are the difficulties with open systems. Okay, your system is the sheep. I don't know why it doesn't. I don't know whether I just
probably the battery is off. So
okay, don't worry. I can do without point. Okay, here, suppose your system is represented by this sheep here. You would like to have your sheep to be described by a cat in the inner space, so to say travel in a quiet sea. And the traveling is just described as the Schrödinger equation, which describes the unitary time evolution of your system. Okay. But this is only an in-principle situation, because in practice, your C is not calm at all, and your evolution is not unitary. And your state is not a cat in the inner space, but rather you have to employ density matrix, and the evolution turns out not to be a unitary at all, since the environment can extract information or energy from your system. Okay, this is a picture here in mind, literally. And this is a more, say, physically oriented sketch. You have a system here which is interacting with the environment, and since this is an open system, you are forced to describe both the system and the environment with density matrices, which are obtained by tracing out the degrees of freedom you're not interested to. For example, given the total state of the system, you trace over the environment to obtain the state of the system, you trace over the system to obtain the state of the environment. Okay, there are a lot of applications for in which all this generic framework can be used. For example, in quantum optics and atomic physics, to describe the so-called the quantum to classical transition, in which you start from quantum mechanics and would like to obtain the macroscopic description of the classical world. In quantum information-oriented application, for example, for storing, processing, or to transfer information from one place to another. In this case, typically you have noise that influences your information processing on transmission, and the noises can be described by an environment acting on the system. And more generally, in every transport processes, in condensed matter physics, in which you typically have noise, of course. And, but I will say more about that. As I told you, the first part is really didascalic. I'm sorry for anybody who cannot do better than I can. But in general, if you start from a state in which there is no correlation at all between the system and the environment, and there is an Hamiltonian describing the evolution of the total system, plus environment, is unitary. So you obtain a total density matrix, which is just the unitary evolved after the initial state. Of course, you can perform a trace of the environment to obtain the state of your system, the system you are interested to, and the system you can measure, the system you want to abstract some property. And of course, you can perform the trace at the initial time to obtain the initial state of the system, and you can perform the trace at the final time to obtain the final state of the system. And you can try to relate directly these two states by a dynamical map. So we call phi of t the map that relates the initial state to the final state. So this is a way to avoid the interaction with the environment, to avoid the microscopic description of the environment, of its state and its evolution, because you are interested in the system, so you don't want to have a lot of details. You cannot extract from measurements. Okay? And so we are led to define this dynamical map, which is essentially a trace of the environment or the unitary evolution. And this map is completely positive and trace preserving. The acronym is CPT map. This means that you cannot lose probability, and even if the system is coupled to something else, nothing should happen to the probability of finding the system in some of its states. Okay. So this is a general definition of the dynamical map phi. And for quantum Markov processes, you typically assume that there is a separation of time scales. That is the typical time scale for the fluctuation of the environment is much shorter than the time scale, the typical time scale for the system. This is the relaxation time scale, but it can be also the phasing time scale. If this condition holds, then a very straightforward approximation gives you that the dynamical map is given by acquire semi-group property. Okay? So that the composition, if you evolve from 0 to t, and then you evolve from t to t plus tau to obtain the final map here, you can write this by just the product of the two maps. Okay? So essentially without memory of the previous evolution. Okay? If this is the case, then the map is an exponential, and you can define a Liouvillean here, and so write a master equation for the state, which is in the so-called Limblad form, but in fact should be called the Riddick-Kosakowski solution, because we are going to players discussing this stuff. And the generic Limbladian here, it just gives a unitary evolution, so the interaction with an effective Hamiltonian, which can be modified with respect to the system itself, plus a so-called dissipator part, in which there are rates for transitions dictated by these operators A. So in practice, in this Markovian approximation, the evolution of each quantum system can be described as a combined unitary evolution plus some dissipation. So in general, some transition taking place into the environment which influence the system by this so-called jump operator. So in the system, jump will occur with some rate gamma I. These rates are positive constants. This should be clear from the definition of what is a rate in general. So probability per unit time. So you expect this positive, but in fact, since this is formal, it can happen sometime that these coefficients here are negative, and I will.
The reflexive operator is written in terms of the step operator.
Yeah.
H.
You mean H
is written in terms of the H?
In parts, yes. This can contain, this is typically the original Hamiltonian for the system plus some term which is related to Lamb shifts or something like that. I mean, the shifts in the system induced by the interaction with the environment, which can be written as Hamiltonian terms. Plus there are this term here which cannot be written as a unitary evolution. So you are forced to write them in this way. And the mean shows
does the Hamiltonian include the saturated A, dagger A, or not? The Hamiltonian H includes the saturated or not?
In general, I mean, these operators are just jump operators. Okay? In general, this Hamiltonian has the original system Hamiltonian plus some Lamb shift, which typically is A dagger A, but not always. Okay, it depends. Okay, it can depend. Okay? Typically, the Lamb shift is A dagger A, if this is the question, but this is not always the case. Okay, so this is say the general theory for quantum Markov processes. This has been developed essentially in the 70s, and from a mathematical point of view, everything is clear. The fact that the map constitutes a dynamical semigroup gives a series of properties which can be used. But the condition for to be fulfilled for the Markovian dynamics, namely the fact that the fluctuation of the environment are very short time, the environment is very short correlated time. Typically, this means that the environment is a white noise. Okay? When the environment is a white noise, then the Markovian dynamics is obtained even without approximation. When the environment is color and its correlation time is not so short, there's not so, its correlation do not decay so rapidly, and so various things can happen. For example, correlation function of higher order with respect to the second order, which appears in the Markovian case, can come out, and there can be revival times, especially for finite reservoir, and there can be generation of entanglement between the system and the environment, which creates, say, definitely generates non-Markovianity in the evolution. Okay. Various methods have been developed to deal with these cases, but I don't want to get into this details. The question is, we want to concentrate on non-Markovian dynamics, and in particular, first of all, we ask one could ask, what is the key feature of non-Markovian dynamics? This question can be it's apparently a stupid one coming from the classical physics and classical statistical mechanics, but in the quantum domain, there is no clear answer to this question. Okay? So I will give one answer, which is one possible answer, which has been developed in the group by Professor Royer and people in Finland and the University of Turku, and then use it. But this is not the only possible answer. Okay? And the answer is non-Markovian means that the system keeps memory, in particular the coherence, the quantum coherence of the system keeps memory of its past evolution. And in this term, it is possible to define non-Markovianity in terms of information flow. Will be much more clear in the next slide. And thanks to this information flow, whenever information comes back to the system after it has gone out, you can say that dynamics is non-Markovian, and you can define a kind of measure for the amount of non-Markovianity. Why this is useful? It can be useful because in many applications, especially in condensed matter systems, the noise is not white. Okay? So in transport process, you cannot envisage only Markovian transport. But also in so-called quantum biological context, in which you have this, say, chromophore molecule that absorb light and then transfer the excitation in order to gain the energy. Okay, they work in a, say, so-called wet environment, which is far from the Markovian. And also, when you describe the evolution of impurities or atoms or whatever in photonic crystals, with band gaps or whenever the structure of the reservoir is not flat, you are really confronted with non-Markovian dynamics. And typically one is tempted to adopt a kind of effective description in which the environment is replaced by effective Gaussian modes. Okay? But it is not clear how well this works. And giving a measure for the amount of non-Markovianity can be an instrument in order to assess how effective is the description in terms of effective Markovian dynamics. Okay, so from now, for this part I will go to the description of one possible solution to this problem. So I will discuss in some detail one possibility of describing non-Markovianity and to measure the amount of non-Markovianity in a given time evolution, a given dynamical map for a quantum system. And everything is based on the distances in the Hilbert space. Okay. So I'll start with a brief recall of what I mean by distances, and in particular what metrics I'll use. I'll use the so-called trace norm, which for an operator A is just the trace of its absolute value, and the absolute value is just the square root of a dagger A. And for self-adjoint operator, this just means the sum of the absolute value of the eigenvalues of the operator itself. Okay. This norm, of course, induces a distance between two states. So if we have two states, rho 1 and rho 2, describing two possible states of your system, you can define a distance between these two states as 1/2 the trace norm of the difference. exactly defined this way. Why this is relevant? Because okay, there's also some stupid properties of this matrix. If the states are equal, the distance is 0. If the states are orthogonal, the distance is 1, and in general, D goes between 0 and 1. Okay? For pure state, it's just 1 minus the overlap. So this is the generalization of 1 minus the overlap to non-pure state, essentially. Okay, there's a lot of properties, so I don't want to, I don't have time to discuss them in details, but this is an example for a qubit. So this is for a two-level system. You can represent the state of a qubit through a block vector, so a three-dimensional vector lying on a sphere. So if these are the block vectors V1 and V2 of describing two states, it turns out that the trace distance between these two states is just half the Euclidean distance between the two vectors. So for qubits, you have a nice interpretation. There's a simple physical interpretation for this distance. This distance, d, rho 1, rho 2, is just a measure of the distinguishability between the two states. The idea is the following. Suppose, one of these two states is prepared with probability 1/2, and there is and you have to select, you have to discriminate between the two. So it is possible to show that with an optimal strategy, the best you can do is to, you can have success in discriminating between the two states with a probability which is 1 plus the distance divided by 2. Okay? So if the distance is 1, the states are orthogonal, there is an optimal strategy in which you can distinguish the two states. If the states are more close to each other, you cannot distinguish with unit probability between them. Okay? So essentially, D is just a measure of the distinguishability between the two states. Okay, why I told you all this? Because now we are going to use this measure here, so this distance between the states, and measure the distance as the states evolve in time. So suppose you have your system interacting with your environment. Your system evolves in time, so its state changes with time due to the map phi, and I mentioned this before. And you want to measure how two different initial conditions become closer and closer. If they become closer and closer as time goes on, you call this process Markovian. While if they at some point start to diverge from each other, you call the process non-Markovian. Okay? This is just a definition. Okay?
And what's the relation of this definition of Markovianity with the standard?
Let me, I'll come to this. So the idea is the following. Try to, there is another mathematical point. Okay? The point is that every quantum operation, that is every map of the type I described before, are contractions for the distance. So in general, whenever you apply a physical operation to a state, if you apply it to both states, the distance decreases. Right? No quantum operation can increase the distinguishability between the states. Okay? This is the key ingredient here. Okay? Now, in the case of Markovian dynamics, the map is a semigroup, forms a semigroup. So if you go from time t to time t plus tau, you just need to add another member of a semigroup, which itself is a completely positive and time-preserving map. So the trace distance can only decrease monotonically. Okay? So the distance between any two states evolved from time t to time t plus tau can only become lesser than the initial distance. Okay? So the idea is that the one I tried to tell you before. If you have two states and you let them evolve, if the process is Markovian, the two states try to become closer and closer to each other. So Markovian processes implies a monotonic decrease of distinguishability. This is the key point. And you can interpret this, but this is a kind of interpretation, so this is so-called unwavering arguments. Okay? You can interpret this inequality by saying that there is some information flowing out from the system. In fact, you have to be very careful with this interpretation, because typically information doesn't flow into the environment. Okay? So there is information flowing out of the system, but this information goes into non-local part of the state, so it is shared between the system and the environment. So it goes out of the system, but the environment doesn't take it. Okay? It's a bit strange, but it becomes entanglement essentially. Okay? So you have information localized in the system, and this information gives rise to entanglement to the coupling of the system class with this environment.
So what happens with this inequality for a unitary transformation? Are we going to dynamics?
For a unitary transformation, this is an inequality. Okay. Now, this is a definition, as I told you. Quantum, we call a process non-Markovian if the derivative of the trace distance between two time-evolved states is greater than 0. So that if this distance increases at some point, okay, for some given pair of initial state at some time. So we call the process non-Markovian if it gives rise to an increase of the distinguishability between the states. Okay. So states are evolving in time, and at some time you can distinguish them more than at the beginning. Okay. Well, in fact, this is not correct, to be true. At some time you can distinguish them more than at some previous time, not necessarily immediately. Okay. This means that there is at some point some backflow information into the system. Okay. So the system gives information out, and then at some point, if this distance increases, we say okay, information comes back, and this gives rise to a memory keeping dynamics. Okay, let me be more specific. Okay, for any system, you can write down a master equation in the so-called time convolutionless form, in which the time derivative of the system density matrix is locally in time. Okay? The generator of the time evolution is again in the Lindblad form. Only the jump operator and the rate depends on time, and two situations can occur. The first one is that in which all the rates are positive. In this case, you call this process a time-dependent Markovian process again. The information flow, that is the derivative of the trace distance, is always less than 0. So information only goes out of the system. But there can occur instances in which these rates becomes negative. So in fact, the wrong point here is calling them rates. Okay? They are not rate anymore. Okay? Only if you try to put the generator in this form, the coefficients here can become negative when the process is non-Markovian. Okay? In this case, it can be shown that the derivative of the trace distance can become greater than 0. And so we interpret this as information going back into the system. Why I'm saying going back? Because it turns out that the rates, there are say some rule of the rates. Okay? In particular, that if you take a generic rate, it cannot start negative. The point is that the integral of the rates in time should always be positive. This is related to the complete positivity of the original map. But if the positive area, once a positive area has been described, you can have negative rates for a short time, so for an amount which is lesser than the previous one. The point is that all the area at any given time should be positive. So the integral of the rate should be positive at every time, but the rate itself can be negative in this case. Okay? So what is now commonly called a negative rate in the literature, in fact, not exactly the rate. Okay? It's just a probability that the process occurs at the reverse, okay? In the reverse direction. The point is that, in fact, for a generic non-Markovian map, the semigroup property doesn't hold, and you can evolve from time 0 to t, and then from time t to t plus tau to obtain the generic evolution from 0 to t plus tau. But this term here is not a map itself. So this is a map here. This is also a map. This is completely positive and trace perceptive. But this term here needs not be a map. Needs not be completely positive. Okay? That's why you can have this kind of stuff. The coefficient become negative. So when the rates are positive, the dynamical map is called divisible in the sense that this term is also a CPT map. But when the rates are negative, this is not a CPT map anymore, and so what I call non-Markovianity should be in fact called, from a precise mathematical point of view, non-divisibility of the map.
But I have a question. For example, there are some processes in biology, but when you have memory effect, but nevertheless probability is positive. So
This we call Markovian.
Okay.
Yeah, this we call Markovian because I mean the distances between two initial states always increase in time. As I told you, this is a definition. Okay. We can use other definitions. Okay. As I told you at the beginning, there's no definite answer. There's no clear consensus over one definition. Okay. I'm just focusing on one of them. But in this process in which all the rates are positive, and so
memory effect important.
well, I mean, the point is that what you call a memory effect can be written as a time convolution explorer for the mass equation, in which all the rates are positive, so the states converge. So this is not truly a memory in some sense. Okay.
So there is no consensus.
No consensus over definition. There are various different definitions. Okay. I will mention another one at a time, but there are at least another three. Okay, but the idea here is just in terms of the distinguishability of the states. Okay, so as I told you, I'm defining Markovianity I'm defining a process Markovian if it gives rise to a loss of distinguishability. Okay, now let's summarize. Okay, so we have defined a trace distance between any two states, which in some sense gives the distinguishability of the states themselves. We have defined the information flux, which is just the derivative of the trace distance. So we say that when this derivative is positive, the information is going into the system, while if this derivative is negative, information is going out of the system. Okay? And then we can define, thanks to this, a non-Markovianity measure, which is an integral over time of this information flux over the region in which it's positive. Okay? So we select the time intervals in which there is this backflux of information back into the system, and integrate, so we evaluate the amount of information that comes back. And this gives a definition of the amount of non-Markovian that is present in a system, in a given dynamical map. This was initially introduced by a paper by Hans-Peter Breuer and other people in PRL in Sistemas, and then elaborated in a subsequent paper. The point, since this is a derivative and you integrate, of course, you obtain as a result that the non-Markovianity measure of a given map is just the distance evaluated at the time point in which the distance is maximum minus the distance at the time in which it is minimum. Okay, so it's the distance at the minimum minus the distance. The distance at the maximum minus the distance at the minimum. So I'm going now to use this non-Markovianity measure and to describe some specific processes.
So this is...
Since, yes, this is state dependent, and in order to avoid the state dependence, we maximize over all possible states. Okay? So there is an optimization, because of course the distance depends on the initial state you have selected. The flux itself depends on the initial state. If you want a measure which is independent of the state, so if you want to characterize the amount of non-Markovianity of a given map, independently of the state on which it is applied, you can optimize over all possible states. So you select the state for which this is the maximum possible. Okay. Now, what I told you also for any kind of map, now I'm going to specialize to the so-called pure dephasing map. For example,
excuse me, for one thing to get one of these examples. How your definition of non-Markovianity characterize two-time correlation function?
Yeah, the point is, it is not related to point correlation function. So I'm not related to that, because in general, the point is that, I mean, go back. Here. Okay. These coefficients here, gamma I.
The point is you cannot write that.
Sorry?
That you could not write the revolution equation in the form of a master equation.
No, you can always write this.
Not for two-time correlation.
You mean?
You need to define a probability at two times.
Right. You mean, okay, instead of describing the evolution of the state, you want to describe the evolution of correlation themselves. Okay.
But
You cannot write
the
right.
rho is a probability at a single time.
Right.
If you want to have short probabilities at two times,
Okay.
you cannot write it like that.
Right. First of all, rho is more than probability. Okay,
Well,
that's, yeah. But okay. So I entered your question in the wrong way. So let me. Okay. When the process is Markovian, then you can write this, right? Because of the quantum equation here. When the process is non-Markovian,
I guess you can.
well, I'm not sure.
Class in the leaf.
Because even when the process is non-Markovian, you can write the time evolution of the state in this form, this time convolution.
Yeah, but this is not enough then to calculate.
Yeah, this is not enough to calculate the correlation function, to time correlation function. So you need the amount. Okay, so in general, when you if you want to consider the time correlation function of the system, I'm not sure. Because
Obvious.
no, really, this would be something to investigate, of course. What I intended your question in the wrong way because I was understanding the correlation function from the environment. Okay. And they are in fact related, and that's the point. But okay, in fact, the correlation function for the environment enters here. Okay. In the case you are Markovian, only 2-point correlation function are important. While if you are not Markovian, this can contain n-point correlation function in general. So it's in general a series of terms, usually. Multiple correlation function, but it should be related to the correlation function of the system. Only I know the answer, so okay, I was going to specialize, so now let's concentrate on a specific process in which the system doesn't lose energy to the environment. Okay? You know that in the quantum case, interaction with the environment can occur even without dissipation, so even without relaxation, but only coherence can be lost. This is called pure dephasing because the energy of the system and the population of the energy level of the system remain unchanged at the time, while the coherence of the error terms in the systematics are quenched, are reduced in time due to a decoherence factor, and this decoherence factor is in fact related to the time evolution induced by the different state of the system itself. So the point is the following. Suppose that the system Hamiltonian commutes with the interaction Hamiltonian. So you have, in general, the Hamiltonian is given by the sum of 3 terms, as I showed before. So there is an Hamiltonian for the environment, an Hamiltonian for the system, and an interaction term. Suppose the interaction term commutes with all the rest, okay? with the system Hamiltonian. Okay? So you select an eigenbasis for the system. This basis doesn't change in time. The probability of occupying this state doesn't change in time. Only the evolution of the environment depends, is conditional on the state of the system. So if the system is in state alpha, since this is an eigenstate of the interaction Hamiltonian, the environment evolves in time with an effective Hamiltonian, which is its own Hamiltonian plus this average. So in the simplest case, it's the case of a qubit in which you have 2 different states, named 0 and 1. There are 2 different Hamiltonian, one in which the system is in 0 and the other in which the system is in 1. And the decoherence is due to the fact that these 2 Hamiltonian are different. So if the environment starts in a given state phi, it evolves in time with h1 or with h0, and if this overlap is non-1, then you lose coherence to the environment. Okay? So this is the generic case of pure dephasing. Now the point is that in the case of pure dephasing, you typically employ a specific quantity to characterize the dynamics, and this quantity is the so-called Loschmidt equal. The Loschmidt equal is just defined as the square of the decoherence factor I introduced before. So it's just a square. This is essentially a green function. Okay, so this is a green function for the evolution of the environment. So you take the environment, let it evolve, and compare this evolution with the evolution in the other case. So in a sense, this remembers you of the idea of Loschmidt, in which if there is reversibility, this should be 1, because if you go on and then come back, if there is micro-reversibility, the overlap should be 1. But in fact, you can go on and come back with your system in 2 different states. And this gives rise to reversibility, because then the system state changes in an irreversible way. Okay. For this reason, this is called Loschmidt, just to remember about the Loschmidt patterns. Okay, in this case, you can write down, say, a master equation in the liberal form, in which the rate depends on the derivative of the Loschmidt. Okay? This can be written down. This is essentially a time-dependent lamp shift for the system, and this is a rate. And of course, now you see that if the derivative of L is positive, then the rate is negative. We are linked to non-Markovianity. Okay? So we have a direct link between non-Markovianity and the Loschmidt and the derivative of Loschmidt if you want. Okay? And in fact, it's easy to evaluate trace distance in this case, given only 2 states the trace distance optimized among all the possible states. So you select the optimal states that maximize the trace distance, and it turns out that the maximum trace distance between these states is just the square root of the Loschmidt. And then, of course, the non-Markovianity measure is just a sum of the various square root of the Loschmidt in times in which is. So the point is that if the Loschmidt only decays in time, the dynamics is Markovian. While if the Loschmidt has some oscillation, you take the minimum and the maximum of this oscillation, and you obtain a non-Markovianity. So a given amount of Markovianity. This is generic. And in fact, before going to a very specific example, and let's stop. What I wanted to mention is that I'm discussing about information going out and going in. In the case of pure dephasing, it's easy to understand what kind of information it is. And in fact, it is a phase information for the system. And you can understand it in the following way. Suppose you prepare your system in a given state. I select this state for some specific reason. I don't want to enter because I don't have time. And then suppose you want to encode some phase information to your system. So you apply a rotation, okay, of an angle theta. So you are encoding this phase information into your system. And then let the system interact with the environment and try to estimate the phase after this interaction. Okay? So the point is, you encoded some information, your environment is disturbing the system, and you try to extract this information. Okay? So any unbiased estimation of this variable theta is bounded. I mean, the precision of any unbiased estimation is bounded by the so-called Kramer-Rao bound. The variance of any estimation is always greater than 1 over the so-called quantum efficient information. Okay? So this f of t gives a description of how much extractable phase information remains into the system. Okay? The larger is f, the more you can extract from the information that has been encoded into the system. Okay, it is possible to evaluate the efficient information. It turns out that the efficient information in this case just equals the Loschmidt. So that if you evaluate the flow of information in terms of the efficient, the derivative of the efficient information, the same ingredients enter the rate and the Loschmidt. Okay. So when the rate is positive, information is going out, while the rate is negative. Exactly as before. So the information I'm talking about is in fact phase information in the case of pure phase dynamics. Okay. My last slide, because I think it's time to stop. Because you said we just applied this to a specific case in which we have a pure dephasing of one two-level system coupled to a chain of spin. And we took for the environment, so here, the green ball here is the system, while the brown ones constitute the environment. So the environment is described by the so-called EC model, quantum EC model in transverse field. And this model is known to have a quantum phase transition. Because you see here, the environment Hamiltonian contains two terms, and external field terms, which when lambda is large, it's very large, it tries to orient all the spins parallel to the field. So the field is, is along x. So all the spins point along x when lambda is very large. On the other hand, when the exchange interaction is very large, here, this J, you can minimize the energy by letting the spin to be parallel along the z direction. Okay? So the two terms have opposite influences on the system, on the environment. Okay? And it turns out that when J is equal to lambda, or when lambda is equal to 1, so when the two terms have the same strength, there is a quantum phase transition in which the ground state changes abruptly from one situation to the other. The idea was to check whether the non-Markovianity, by looking at the dynamics of the system, which is interacting with this kind of environment, and looking at the non-Markovianity of the system, of the map describing the time evolution of the system, we can extract information about the quantum phase transition. And in fact, the answer is yes. I'll just give you a very short summary of the situation, because it turns out that at the critical point, when the phase transition occurs, the Loschmidt decays monotonously in time. While if you go in the ordered phase, the Loschmidt has these oscillations, and if you go into the disordered phase, the Loschmidt again has oscillations with a stationary around a stationary value, a non-zero stationary value. So since there is oscillations, the non-Markovianity measure is non-zero far from the critical point, while it is 0 at the critical point. Okay? So the non-Markovianity measure can be thought as an indicator of quantum phase transition. Why is so? The point is that when you reach the critical point, the environment is becoming stiffer and stiffer. Okay? Because at the critical point, every fluctuations takes place on a longer and longer time. So the environment does not react. And since it does not react, it can give information back to the system. Okay? So this is the intuition beyond this result. At the critical point, the environment is stiff, does not react, does not give information back, and so the evolution of the system is not common. So if you look at the system coupled to an environment, you can detect whether the environment is critical or not by looking at non-Markovianity. Okay, and I think I can stop here. I had other examples, but I don't have time to discuss them. Okay, I can choose another one. Just to we'll try to relate this behavior, the behavior of the Loschmidt and the non-Markovianity, to the so-called orthogonality catastrophe, which is something happening on a many-body system in the case in which you act on the system with a subtle perturbation. Okay. This was a concept introduced by Anderson now 50 years ago, more or less. And the idea is that the original idea was that developed by Nosier de Dominicis, this is M&D theory, and the idea was, suppose you have a valence band for a metal, and suppose an X-ray produces a core hole in the metal itself. So you suddenly produce an extra term in the Hamiltonian due to the interaction of all the electrons with the core hole. So suppose one electron is let out of the system due to the X-ray, and so all the other electrons will rearrange themselves. Okay? This process is called electron shake-up. So the electron will rearrange themselves due to this shake-up. But the point is that since the hole is very deep in energy, it can have a very small effect on each electron. Okay? The point is that, and here is why the term catastrophe. The point is that since there are many electrons, each of them contributes a given small amount of change. And if you look at the overall change of the system, it can have a huge impact. So even if you have a small interaction because one electron has come out in a system that has many electrons, this can change completely the state of the system due to this shake-up. due to the fact that although the interaction with each electron is small, the interaction with the whole system can be catastrophic. And the idea is to try and reproduce this kind of effect in a more controllable experimental setup in which you have cold atoms in an harmonic thought. So suppose you have fermionic atoms interacting with an impurity. And the impurity itself is a qubit, and it undergoes a dephasing dynamics. And okay, we evaluated all the stuff, and I don't want to enter into the details. The point is that the spectrum of the excitation can become simple. In the fermionic system, this interaction can be excitation, quasi-particle excitations. And the energy distribution of these excitations can become singular depending on the strength of the interaction and on the Fermi energy here. And well, this singularity index signals the fact that the catastrophe is occurring or not. When this index is compressed between 0 and 1, there is the catastrophe occurs. While if this index is greater than 1, nothing catastrophic occurs in the system. So we have evaluated the non-Markovianity measure for the impurity and found out that the behavior of the system becomes Markovian once there is nothing singular in the language. Again, and the physical intuition is again the same. If the system is singular, many quasi-particle excitations come out, and they can respond to the system, and the system dynamics is non-Markovian. While if you are outside this singularity region, this cannot happen, and the behavior of the system is Markovian. Okay. This is, say, in 3 minutes another example. I'll leave it at everything. So, to summarize, the main part of the talk has been to discuss a possible way to measure non-Markovianity, so to measure the amount of non-Markovianity in a given dynamical Markov system. Then we try to link the non-Markovianity to the Loschmidt in the case of pure dephasing, and show that if the environment is a critical one, at a critical point you can have Markovianity. Okay, then I briefly mentioned include the orthogonality capacity. And thank you very much.
Any question from students? There are no questions from students? No?
You have an example with the XY model. Can you show us something about the XY model?
Yeah, I can. Okay, it takes time. Okay, the point is that the idea here, suppose you have a system interacting with an environment. Again, we choose spin environment because spin environment are non-linear. Okay, so you have something special in the case of spin environment. Rather, if you select, as typically done, a bosonic environment, then the Gaussian approximation is often good. Okay, not always, but not. In the case in which your environment is non-linear and the interaction is not the empirical phasing one I told before, the situation is much more complicated, much more complex. So we call this non-Markovianity phase diagram, which depending on the parameters of the system, various things can occur. I go directly to the graph. For example, if you look at the non-Markovianity as a function of the detuning between your system and the spin of the environment, it turns out that there are regions in which you are Markovian, while there are regions in which there is a peak of the Markovianity and there is a region. Okay. And this non-Markovianity region, say blue ones, are quite different from each other because here an equilibrium state is reached, while here no equilibrium state is reached. So information still remains on the system and it bounces back and forth between the system and environment. While in this case, depending on the tuning, information goes out at some point and never come back. But there is a transient time in which there are oscillations and a long time the Q is flat. Okay. So there can be a Markovianity region and two different non-Markovian behavior, depending, for example, on the tuning, but there are other cases depending on the coupling. There is a quite rich scenario in the parameter space, which is a system with a rich parameter space in order to try and check various properties. For example, one specific property is that by increasing the size of the environment, the non-Markovianity measure increases. And this is something I mean, one could expect that if there are many decoherence channels, if your system can lose information in various directions, okay, you expect that at the end, when the number of directions which you can lose information becomes larger and larger, you become more and more Markovian. I mean, your evolution becomes more and more Markovian. Because all the various information all the various parts of the information that are lost in various directions should refocus together in order to reconstruct the coherence of this system. But in fact, it turns out that depending on the interaction, in particular, in the case of the XY interaction, this refocusing can occur, and the amount of non-Markovianity increases with the number of coherence channels. Of course, this is not generic. Okay? Generically, it goes to zero, like in the second and third area. But there are instances, special instances in which there are value labs. Okay.
I would say that the maximum non-Markovianity would be when in the state goes back to where it was at the beginning.
Right. If you look, for example, if you have radio oscillations, this is highly non-Markovian. The non-Markovian measure can go to infinity. Okay? Because you lose information, but then you reacquire it, then you lose it again, and then you reacquire it. So in this case, unitary dynamics, in the case of radio oscillation, can rise to a huge amount of non-Markovianity.
So in a sense, the right measure is something which is the overlap with what's at the beginning.
Not always.
Instantly overlap. Not that integration.
Not always, because this is state dependent. So the initial state. So depending on your initial state, you can have oscillations or not. And this is true for the case of unitary evolution. In the case in which the evolution is not unitary, you cannot look at the overlap itself. It gives different stuff. Because, for example, the state can become closer and closer, while in the geometric view as we did before, but simply because they have a phase difference. Okay, suppose you have to keep a state that rotates in the plane with a different angle, so they follow each other this way, but they stay at even distance. And this we call non-Markovian because some information remains. But if you look at the overlap, okay, the overlap is always the same, so it doesn't change with time. Okay. So this doesn't give you exactly what non-Markovian means.
Just a curiosity, okay, I'm doing no work in this field, so I'm thinking, sorry, but the relation of non-Markovianity, does it have some connection, some relation with chaos, because the two states that can get closer or not, between partners?
I think so. I know there has been a paper by people discussing non-Markovianity in connection with the quantum chaos. The point is that typically, for example, in the case of pure phasing, typically the Loschmidt is a power law behavior in the case of chaotic system. And so you probably can extract from this information about non-Markovianity. I don't know. Yeah, I think the intuition.
For unitary evolution, the distance between zero. Because it's linear, it's true, there's certain.
And so, the point is that
But
you can define the Markovian for non-distinguishable dynamics.
Chaos implies non-linearity.
And this is
Quantum
yes.
mechanics is linear.
Yes.
no, but you can take a system that by itself is it's a quantization of a classical chaotic system, and then it is interacting with some environment. So you have an open quantum chaotic system.
Quantum chaos. Oh, yeah.
And then the point is that in this case, the Loschmidt has special properties. For example, the Sweden transform is a right Leibniz distribution variable of range. Or I think at the onset of the chaos, it changes its character. And probably it's possible to relate the properties of the Loschmidt to the Markovianity as we have done. But I've never did it, so.
Are there any other questions? Maybe just last one. At the beginning, you were mentioning these things about transport, so the fact that non-Markovian, you need to study this kind of non-Markovian system because there are examples in transport, biology, and in the crystal environment. So you know if in transport phenomena,
for example, transport phenomena typically is affected by one over F noise, which is the most non-Markovian noise you can imagine. Okay? And still, people is using Gaussian model in order to try and give a description of transport in the presence of one over F noise. One could try and evaluate the amount of non-Markovianity for that illusion to see whether this Gaussian, effective Gaussian Markov maps can be useful or not in this case. So the idea is, when you have a system that is truly non-Markovian, you can, unavoidably non-Markovian, okay? Because the environment gives rise to noise which is not found in this distribution. And you could try and see how much non-Markovian it is, and if the amount of non-Markovianity is small, then probably an effective Gaussian model works, while if the amount of non-Markovianity is huge, then probably any effective Gaussian model won't work. That was the interaction.
so thank you. Let's have a speaker again.
Yeah, my question is